Alrighty. All right, hopefully everyone can see. All right. So we're coming up on the last few weeks of the semester. So the topics that we're going to cover in these last few lectures, we're going to do electrical conduction today. We're going to talk about the difference between conductors and insulators. Well, we did that earlier, but going along those lines, we're now going to talk about currents in conductors, and then we're going to talk about capacitances in dielectrics. Okay, so we're going to focus more on the conduction today. We'll start getting into some of the stuff about the charges at interfaces, and then by Wednesday we will have covered capacitance as well. So that's the goal. So just to give everyone a little bit of a recap from before. All right, so a little bit of a recap from before. We were talking about the differences between dielectric materials and conductive materials. All right, so let me jump ahead here. Yeah. What's the main difference between dielectrics and conductors? And you don't need to take electromagnetics to know this answer.
Charges can move.
What's that?
The charges can move.
Charges can move, exactly. So in conductors, charges are loosely bound to the atoms. So when you apply an electric field, the charges actually hop from atom to atom. So there's a net movement of charge. In dielectrics, the electrons are more tightly bound to the nucleus. So in a dielectric, if you apply an electric field, the electron cloud surrounding the nucleus, the electron cloud can move a little bit, but the electrons are still attached to the atom. All right. So what happens in a dielectric is when you apply the electric field, that movement, that net movement of the electron cloud causes a dipole to be formed, electrical dipole. Right. And that's one of the origins of capacitance, because when you apply an electric field and all these dipoles line up, that dipole effect is basically what gives you an enhanced electric field inside the material. But there's no current. Okay, so this is what a capacitor looks like. A dielectric material, you put an electric field across it, the dipoles line up. Okay, so this is ultimately what's going to become a capacitor. On Wednesday, we'll actually derive the formulas for capacitance. Now, when we talk about conductors, so we're going to talk about conductors in static fields, and conductors when they're not connected to the circuit, and conductors when they're connected to the circuit. The key point with conductors is that charges can move. Okay, the fact that charges can move within the material is what really determines virtually all the properties of the conductor. So we're going to talk about this type of behavior when it's not connected to the circuit and when it is connected to the circuit. Actually, we talked about this in class last time, and I just want to remind everyone that a metal sphere, if you put charges on it, or not just a sphere, but any metallic object, if you put charges on it, if you charge it up, those charges will migrate to the outside. Does anyone remember why those charges migrate to the outside?
Because they're all repelling each other?
They're repelling each other, exactly. Charges will repel each other in any type of material, right? In a dielectric material, like charges will repel each other, right? You have a positive here, you have a positive here. But the key difference is in a dielectric, those charges can't move. Okay? In a conductor, the charges can move. So if you have positive charges on there, those positive charges can move away from each other. They move as far away from each other as they possibly can. And that's what causes them to build up on the surface. If you look at this metal sphere, for example, if you charge it up positively, these positive charges are moving as far away from each other as possible. And so they distribute themselves on the surface of the sphere. As a result of that, something interesting that happens is that the electric field inside becomes zero. The way these charges are arranged, you can imagine that the electric field inside the material will be zero. Another way to think about it is that another way to think about it, and we'll get to this in a second, is that J is equal to sigma times E. In a conductive material, this sigma is infinite, and so the current density becomes 0. In a perfect conductor, the sigma goes to infinity, and the electric field basically goes to 0. Okay, we'll come back to that in just a second. All right, now, so we're talking about current today, okay, and I want to focus our discussion on current. How much of this did we talk about last time? Not much. Okay, let's start from here then. All right, so we're going to skip over the Van de Graaff stuff because I know that we covered that last time. Electrical conduction. Basically what we're going to do today is we are going to talk about Ohm's law from the electromagnetics perspective. Where did this come from? What's happening at a deeper level? And ultimately, how do you derive Ohm's law with electromagnetics? All right. All right, first of all, what is current? Electrical current is the movement of charge through a conductive material. And unlike dielectrics, the conductors can support electrical currents, meaning in conductors, charges can move through a material. Units for current is amps, which is a coulomb per second. And when you say a wire has 5 amps going through it, that means if you look at this cross-section, if you cut the wire and you look at this cross-section, there are 5 coulombs per second of charge moving through that cross-section every second. That's the definition of current. So Ohm's law says V equals IR. You place a voltage over a wire, you place a voltage over a resistor, you're going to get some current across that thing. So, V equals IR, V is the voltage, I is the current, and R is the resistance. So we are actually going to derive the resistances for different shapes of materials, for different types of materials. I want to remind everyone that there's 2 types of currents. One of the types of currents we study more in ECE 4570. That's called diffusion current. The type of current that we look at in this class and the type of current which is Ohm's law is called drift current. Drift current is the movement of charge due to an electric field. All right, so the questions we want to answer here is what is drift current? How does drift current flow through any type of material, a conductor or a semiconductor? And then how do we actually calculate the resistance of a material? So current density is the current per unit area. So when we think about current flowing through a wire, if we look at this picture right here, all right, there's a bunch of current flowing through the wire, and that current can be thought of as a bunch of small vectors that go that are perpendicular to this cross section, and each one of those vectors is the current density. Okay, it's the density of current. The total current can be found by adding up all the current density vectors. All right, so if each one of these little arrows is a current density at a point in space, then the total current is equal to the surface integral of the current density. So just to remind everyone, just to think back for a second, remember whenever we take an integral, the units changes, right? So the units for current density is coulombs per meter squared. If anyone wants to jot that down. Or I'm sorry, amps per meter squared. Sorry. The units for J is amps per meter squared. So what happens if we integrate J once? What do we get? It gets amps per meter. And then if we integrate it again, so if we do a double integral, then we get amps. Right? So that's the logic behind this thing. J is amps per meter squared. We take the surface integral over the cross section, and we get the total current. Does anyone know why we even bother with current density? This is a simple case where the current density is the same everywhere in a wire like this. But if you have, if you have different types of materials where the conductivity might be different in different places, if you have bends in the materials, other types of geometries, then the current densities can actually be different in different parts of the material. And where you have really, really high current densities is where you build up hotspots. In semiconductors, this is very important. In certain places where you have current running through, wherever you have a really high current density, that's the part of the semiconductor that can actually burn out, because you're generating a lot of heat in that area. We'll talk about joule heating in a little bit. All right, so really quick problem. If we have a current density in a cross-section of wire and it's uniform, the wire has a radius of 5 millimeters. What's the total current? So just as a warm-up problem, because this is a fairly straightforward calculation, I would just like everyone to just quickly do this problem here. You're given a current density and you're given the cross-section of the wire, and I would like you to calculate the total current. You guys need paper back there? Oh, now I'm giving you a hard time. It's good. I know this particular problem seems quite easy, but it's always worth it just to do it. And I'm not just doing this to give you busy work. I'm actually trying to do this to save you all time. If you know how to kind of do the problems in class, then your homeworks will go faster. And I know you all are busy with work and things like that. So that's really the purpose of this. All right. We'll do this. Has anyone found a solution? Yes?
Should be 2.5 pi.
2.5 pi. All right. Let's do that real quick.
10 pi.
So J is equal to 0.1 0.1 amps per millimeter squared. I is equal to the integral of J dot ds. So this is how do I close this? There we go. All right, this is the simplest kind of problem where you have a uniform J. I don't know why it's doing this. Okay. And the radius here was it 0.1 millimeter? Okay. All right. So in this case, since the J is uniform everywhere, this is just going to become J times the cross-sectional area. So it's J times pi r squared. We just have to be a little bit careful about the units here. Is 0.1 amps per millimeter squared. So we want to use millimeters for the radius. So the r here is 5. All right, so our millimeters here will cancel. And so we're left with 25 times pi here times 0.1 is 2.5 times pi. All right, and the units for this is amps. All right, so that was just a quick problem just to get us started here. Now, suppose we have a unit wire with non-uniform current density. Suppose the wire is on the z-axis and the current density is given by J of R equals 5R. What is the total current in the wire? All right, so I'm going to draw this for you. Actually, I'll let you draw it. Let you draw it yourself. It's part of formulating the problem. Okay, So I'd like everyone to start by just drawing this in cylindrical coordinates. Draw the wire, and assume that this wire is made up of a material where the material properties is such that the current density is higher as you go further away from the z-axis. So this is sometimes possible if you have like a semiconducting wire and you dope the outer portions of it. The outer portion of the wire will actually be more conductive than the middle of the wire. So you're going to be using the same formula as before, but now you no longer have a uniform current density.
Same dimensions.
I'm sorry?
Same dimensions.
Oh yeah. I'm so sorry. Oh, yeah. I need to give you the density of. I'm sorry. The radius of the wire. So let's say the radius of the wire is 1. Okay. Radius of the wire is 1. Let's fix that. So the wire is on the z-axis. The current is flowing on the z-axis.
Could be going down.
It's flowing up. You can just assume that it's flowing up. In this particular problem, it won't matter which direction it's flowing, but you can assume that it's flowing up. Yeah.
But then if it's flowing down, that means it's negative.
The direction will be that's correct. But you're asked to calculate the total current in the wire. So current has no direction. Well,
Total current doesn't have a
the total
direction.
current doesn't have a direction. The current density has a direction. So let me quickly show you how to do this one. So in this problem here, okay. So here what we're going to do is assume that we have we're in the cylindrical coordinate system, all right, and we have a wire along the z-axis like this. All right, and the current density is actually larger on the outsides of the wire than it is on the inside. So that's given by J of R equals 5R. Okay, so this is one of those a wire with strange material properties. And like I said before, this can happen if the wire happens to be doped more highly along the outsides than the insides. So how do you find the total current here? Again, you use this formula. I is equal to the integral of j dot ds. Except this time, it's you actually have to do the integral. You can't just, in this problem, what happened is this integral here, integral of j dot ds, just became j times a because j was uniform everywhere. In this problem, j is not uniform everywhere. You can see that j is being given as a function of r. So in this case, we actually do have to do the integration. All right, the j of r, so j is given in the z hat direction. All right, so these vectors, j, are pointed upwards. So they are pointed in the z hat direction, and the magnitude of j is 5 times r. All right. So whenever we do problems like this, I like to just break it down. You've defined JR, and you have the direction and magnitude. Now you want to define DS. So can someone tell me what DS will be? R d phi dr, and direction? Z hat, right. Remember, in this formula, J is a vector, ds is also a vector. All right, so they're vector quantities. Why is this r times d phi times dr? Well, the two variables we're going to integrate, because we are going to integrate over this surface here. All right, this is the ds surface that we're going to integrate. In order to integrate that surface, we need to integrate the variable r to get from the inside to the outside of the side of the circle, and then we need to integrate phi to go all the way around. Okay, so I had a sharper one. There we go. All right, so j dot ds. J dot ds is, they're both in the z hat direction, right? So this then collapses to 5 times r, and then there's a squared factor here because you're multiplying 5r times r, and then d phi dz. All right, so we're going to integrate that. I'm sorry? Oh, d phi dr. Thank you for that correction. D phi dr. All right, so now we're going to integrate this. 5r squared. I'll put the dr in here and then d phi on the outside here. So what are going to be the limits of integration for r? 0 to 1. And then the limits of integration for phi? 0 to 2 pi. Good. All right, remember this d phi here, this can actually come out. It's no longer, we can separate this into two integrals, right? Because this part is not a function of phi, this part is, and so there's no convolution here, so we can bring this out, and we'll have the integral phi is equal to 0 to 2 pi of d phi, and the integral from r equals 0 to 1 of 5r squared dr. And so this will then become 5 over 3r cubed from 0 to 1, and then this will just become 2 pi. So this just becomes 5/3 times 2 pi, or 10 over 3 times pi. All right, so this is an example where we had a non-uniform current density. Any questions about this one? Okay, great. All right, moving on then. The next topic here is electrical conduction. So now we're going to zoom in and look at what's really happening under the hood when there's current. All right? When you go in the lab, you put a voltage on there, you measure the current. This is what's actually happening in the material. A typical material could have one or two types of charge carriers. Does anyone remember what the two types of charge carriers are? Free electrons and holes, right? Holes, you end up getting holes in semiconducting materials. In metals, you're mostly just dealing with electrons. Okay, holes have a positive charge and electrons have a negative charge. Right? There's no protons flying through the materials. Right? The types of charge carriers are electrons and holes. Okay, now, so what happens is that when you put that voltage source on there, all right, you put a voltage source across a wire, or you can model that as a resistor in your circuit element. When you do that, this is what actually happens in the material. The voltage generates an electric field. The larger the voltage, the larger the electric field. And the voltage and electric field are related through the formula V is equal to the integral of E dot dl, negative integral of E dot dl. All right, so when you apply a voltage, you certainly get an electric field. That electric field will cause the charges in the material to move. The positive charges will move in the same direction as the electric field. The negative charges will move opposite the electric field. All right, so if the electric field is moving from left to right, these red colored circles represent holes. The holes move in the same direction as the electric field, and the black colored circles move in the opposite direction as the electric field. The black colored circles are the electrons. Now, both of these types of charge carriers can generate a corresponding current density. And the current density is given by J. Okay, and then J we looked at before. We just sort of represent that as a bunch of circles coming out of this cross-section. All right, the more current density you have, obviously the more the total current is going to be. So this slide is actually showing us the relationship between current density, charge density, and conductivity. All right, these are actually very important and fundamental equations, so it's important that we understand this. So first of all, intuition. As you can imagine, more electric field means the carriers move faster. So if we increase E, these carriers are going to move faster. So what's not covered in your Circuits 1 class is how fast are those charges actually moving. Like we're talking like meters per second. How fast are they actually moving through the material? And it turns out that there's a very nice relationship that describes that. So let's start off with a single charge carrier, a metal. Okay, in a metal, we're talking like copper, silver, gold. Electrons are the charge carrier. The velocity of those charges is described by this nice compact equation. U is the velocity. U is equal to the mobility times the electric field. And why is there a negative sign here? Right, because the electrons move in the opposite direction as the electric field. Now these things both have a subscript E, and the subscript E denotes electrons. Okay, when we're talking about holes, there's a subscript H to denote holes. All right, so this is saying that the velocity is proportional to the electric field, and the constant of proportionality is this thing here, mu. All right, one of the things I just want to make sure that this is often a point of confusion. Don't confuse U with mu. U is velocity. It's a vector quantity, and mu is mobility. Exactly. Mobility is a property of the material that we're talking about. Highly conductive materials tend to have very high mobilities. Graphene is an example of a material that has really high mobilities, so That's why there's a lot of interest in using that as interconnects and things like that. All right. Now, the current density, J, is equal to the current, the charge density times the velocity. Now, I want to explain to you the intuition behind this. Current is moving charge. Imagine these charges just moving through the material, all right? The more charges you have, the higher the current is going to be, right? So that's why you have this rho v here. Rho v is charge density. That's the number of charges you have per unit volume. So the units would be coulombs per meter cubed. All right, and then the second part you have to think about, the current is not just about how many charges you have, but how fast those charges are moving. If the charges are moving very, very rapidly, that also means you have a lot of current. So that's why you have this velocity here. So current is basically the product of how many charges you have, rho v, times how fast those charges move, which is u. All right, and the units for this make sense because J is equal to rho v times u times velocity. All right, the units for rho v, this is coulombs per meter cubed. What's the units for velocity? Meters per second, right. Good. So if you take coulombs per meter cubed and you multiply it by meters per second, you get coulombs per meter squared per second. This is the units for current density. Coulombs per meter squared per second is the same thing as amps per meter squared, because 1 amp is 1 coulomb per second. So the units work out here. Whoops. All right. All right. Now, so we've gotten this far now. So the reason there's a negative sign here again is because we're talking about electrons. Okay, so rho v times mu e times E, and that's equal to sigma times E. So sigma, this is a definition here. Okay, we are defining sigma as negative rho v times mu E. Rho v is the number of electrons per meter cubed that the material has, and the mobility represents how fast the electrons move through the material. By the way, if you want to jot this down, this is the units for mobility. Units for mobility is, so mu is given as centimeters squared per volt second. This is mobility. I'm sorry? It could be given in meters too. It depends. Like sometimes it's given in meters squared per volt second. Sometimes it's given in centimeters squared per volt second. Yeah. So just be careful of that. So I'll just denote here that it could also be given in meters squared per volt second. I'm sorry? Well, it depends. Like what some charts may give it to you in meters squared per volt second, and some charts may give it to you in centimeters squared per volt second. So whichever one you have to make sure that the units that you use in solving the problem corresponds to the constants that you've been given. But if you want to convert it, yeah, you can multiply it by, if you want to go from centimeters squared to meters squared, you can just do that unit conversion. Did I answer your question?
So the centimeter squared times volt second is simply for reporting. That's the scale that you're normally working on. But if you're going to calculate, you want to do everything. You want to match your units regardless.
Yeah, exactly.
So for the
So
final answer,
in
that's what I-
semiconductors, for example, when you're dealing with semiconductors, people doing semiconductors love to use centimeters instead of meters. Don't ask me why. Physicists like to use meters, MKS, for everything. So.
When would you want to use
So wires that had different densities in the outside relative to the inside.
Sometimes it happens when you're doping semiconductors. So semiconductor wires are often formed by a process called diffusion. This is where you start off with silicon and then you diffuse boron or some impurity in there, which makes it conductive. Since the impurities are coming from the top of the semiconductor is actually more conductive than the bottom of it. So that's the situation where you may have non-uniform conductivity, non-uniform current densities.
Mobility change with temperature.
Yes, mobility changes with temperature. But we're not going to really focus on that much in this class just because that's more of a topic for electronics too. But yeah, good memory. All right. So this conductivity is equal to rho, the charge density, times basically how many charges there are in the material, multiplied by how fast charges move through the material. So this is a material property, and we can look it up on a chart. All right. Now, if there's two charge carriers, then you have two types of current. UE represents the velocity of the electrons, and notice that it has a negative sign there. And UH represents the velocity of the holes. Those are those red circles. So that's UH times E. UH is equal to mu H times E. Now keep in mind that electrons and holes actually have different mobilities. I'm mentioning these things to you right now. We won't have that many problems involving semiconductors for this class. I just want you to know that it's there. So in this case, the current density is equal to the sum of the currents due to electrons and holes. We have to consider both components. So J is equal to negative rho V times mu E times E plus rho VH times mu H times E. So this first term here is the current due to electrons, and the second term here is the current due to holes. And again, we simplify that, or we make that in a compact form. We call that sigma times E. In this case, sigma has two parts to it. It's the conductivity due to electrons and the conductivity due to holes. All right? But you notice in both of these cases, J is equal to sigma times E. All right? So remember that. That's a very important relation. J is equal to sigma times E. The sigma will depend on what material you're talking about. Okay. Do we want to do this problem? I think I'm going to skip this one over in interest of time. We'll come back to it. Let's do a simpler problem at the beginning. 2 millimeter copper wire with conductivity 5.8 times 10 to the 7th Siemens per meter and mobility 0.0032 meters squared per volt second. All right, you see you're given the friendly MKS units in this problem. A 20 millivolt per meter electric field is applied. Find the volumetric charge density, the current flowing in the wire, electron drift velocity, and the volume density of free electrons. The reason I have all the solutions here is because this is just something I want to go over with you very quickly. You know, we won't bother spending that much time on just writing out the solutions. I want to explain these things to you conceptually. So 2 millimeter copper wire, you're given the conductivity, you're given the mobility, and you're given the electric field. All right, so this problem is really about just using those formulas that you were given in order to figure out the charge density, the current density, and the total current, and so on. So let's look really quickly how to do this, and you'll have a homework problem that's exactly like this, so you'll get some practice doing it there. The reason I'm not spending that much time on this problem is because it's pretty much just plug and chug. In this particular problem, it's a single charge carrier, so it's metal, and so you're just using these formulas. All right, so the volume charge density, the way that you find that, let me zoom in here. The volume charge density is just equal to the conductivity divided by the mobility. All right, and you divide those two, these two numbers that you're given, and the charge density is 1.8 times 10 to the 10 coulombs per meter cubed. Be careful with the units here. Just make sure that you know what the units should be. Charge density is always coulombs per meter cubed. Mobility is meters squared per volt second. Current density is amps per meter squared. J is equal to sigma times E. So you're given the sigma in this problem, and you are given the current density in the problem. So that, I'm sorry, you're given the electric field, sorry. 20 millivolts per meter you're given. So this gives you the current density. Any questions so far? All right, so here the total current. This is a wire that has uniform current density everywhere, so the I is just equal to J times the cross-sectional area, and J times pi r squared. I don't know why the book does pi d squared divided by 4. It's the same thing as pi r squared. And the total current here is 3.6 amps. The velocity is equal to the mobility times the electric field. All right, this comes out to negative 6.4 times 10 to the negative 5 meters per second. This gives you an idea that the charges are actually moving pretty slowly in this problem. 10 to the negative 5 meters per second. That means in 100 seconds it's moved a millimeter. That's pretty slow movement of charge, right? That's not always the case. Sometimes these electrons can move through a material very rapidly at higher levels of current. Okay. And the last part here, the volumetric charge, the volumetric electron density. They're asking you in this problem the number of electrons per centimeter cubed. The way you find that is by taking charge density, which has coulombs per meter cubed as the units. You divide that by coulombs, the charge on one electron. And so this gives you the number of electrons per meter cubed. 1.13 times 10 to the 29. That's a lot of electrons. Did anyone remember Avogadro's number? Yeah. What does Avogadro's number represent?
The number of electrons in a mole.
Or the
number of electrons in a...
The number of atoms in a mole, or number of molecules in a mole. Yeah. But, like when you're talking about atoms and electrons, you end up talking about really crazy high numbers like this. Okay. So this is the number of electrons you'd find in a square meter, or a cubic meter of material. All right. So I went through that pretty quickly. I imagine you can look back at that at the lecture notes. All right. Now a little bit of intuition. So I was hoping that this chart will give you a little bit of intuition here. Electric field is what pushes these charges along, and then you end up developing this current. So that's where Ohm's law comes from. You apply voltage, you get a current. This is a cartoon that I think I found or a student had shared with me. This represents what an ohm is, what a volt is, and what an amp is. If this helps you understand it, great. If it confuses you more, just ignore it and just look at it as a cartoon with a bunch of funny looking characters. Why is this guy pushing the amp? Because the voltage, when you put a voltage on a wire, the voltage is basically what pushes electrons through the wire. The voltage generates an electric field. Charges move in the presence of an electric field. Okay, this is very similar to water moving through a pipe. All right, if you put high pressure on one end of the pipe, the water moves, right? If you don't put any pressure on the pipe, what happens? The water just sits there, right? So the same thing can happen in a wire too. If you put charges on that wire, but you don't apply voltage to it, those charges just sit in the wire. They don't move. Okay, so that's the intuition that this is trying to get. When you put a voltage on the wire, you're actually creating that electric field that pushes those electrons through the wire. Very similar to like if you put a high pressure on a pipe, that pushes the water through the pipe. Now, the second part here is the amp. Okay, the amp represents the moving charge. All right. So the volt is trying to push the amp or push the charges through the pipe. And the ohm is what we call the resistance. All right, this is a nice analogy because if you think about water flowing through a pipe, if you have a narrow constriction in the pipe, like if you would ever take a garden hose and like kink it shut, you're increasing the resistance in that portion of the pipe. Similarly, in a wire, if you have like a really thin section of wire, that portion of the wire has higher resistance than the wider portion of the wire. This is why in your house, like, you know, if you know that you're going to be carrying lots of amperage, those wires are pretty thick, right? You know, the ones that are designed to carry like 10 amps, 100 amps of current, those wires are very, very thick.
So if they apply, like, let's say in the house, they apply like a high ampere wire, like the switch closes.
So if you try to apply a high amount of amperage to a wire that's not designed for high amperage, you would actually end up heating the wire and melting it. So the circuit breakers are there to protect that from happening, to prevent that from happening. So the circuit breakers have something called a fuse. And the fuse is actually a really thin wire that burns out when you try to run too much current through it. So when that fuse burns, or when that fuse breaks, then the current, the circuit is basically off after that. The fuse boxes were the old style things. The circuit breakers work in a slightly different way. They actually have a different way of detecting the amount of current, and when it detects it's too high, the circuit automatically switches off. Yeah.
Just like cool water and voltage, the drain is the resistor.
Mm-hmm.
And you can open up what you want.
Yeah.
And flow into it.
Yeah, that's another way to think about it. So in that case, like the pressure on the water is hydrostatic pressure, and that's driving it through the drain. But if you have a really small drain that has a lot of resistance, so there's not much water that flows through there, not much current that flows. So the ohm is what resists the current from flowing through the pipe. I think, Justine, did you have a question a little while ago? I thought someone had raised their hand over there, but I just wanted to finish up this discussion before taking questions. Okay, all right, no worries then. We'll just continue. So Ohm's law is V equals IR. Now, in the electromagnetics world, this is another form of Ohm's law. You've learned V equals IR in your previous classes, but in electromagnetics, the definition of Ohm's law can be given in terms of J and E. J is equal to sigma times E, and that's basically the same thing that you've seen in these previous slides. J is equal to sigma times E. I'm putting another slide on it just because I want to emphasize the relationship between V equals IR and J equals sigma E. It's really an analogous relationship, as we'll see. Now, conductivity in materials. So what is the sigma? We've already derived it, so you can see where these formulas come from, but this is just a summary. If you have metals, then sigma, the conductivity, is just due to electrons. So it's Q times mu n times n. N is the electron concentration. All right, the slides before was showing rho VE times mu. So rho VE is just equal to Q times N. A general semiconductor which has electrons and holes, the conductivity will be Q times mu N times N plus Q times mu P times P. This is the conductivity. This is the conductivity due to electron flow, and this is conductivity due to the flow of holes. If you have an N-type material only, then you're only going to have electrons in there. So Q times mu N times N, similar to a metal. And then if you have a P-type semiconductor which only has holes, very few electrons, and this conductivity equation will look something like this: Q times mu P times P. All right. So this is something that this chart will just be something that you can use to figure out problems. Okay, we don't want to spend too much time on that. This chart shows the conductivity of some common materials, and since the question came up earlier, in this chart the conductivity is given to you in MKS units. Siemens per meter is MKS units, so you don't need to do any type of conversion to centimeters, or conversion from centimeters rather. So if we look at the conductivity of these different materials, you can kind of get an idea of, how good a conductor these things are. Remember, the conductivities are coming from the fact, two things of the material: how many charges the material has, and then what the mobility is, meaning how fast the charges move through the material. You can see that these metals, the silver, copper, and gold, are very good conductors. All right, this is why you sometimes see silver paste being used in circuits and different types of like solder paste. Sometimes you can even buy the silver paint right now, where you can paint circuits, you can paint wires. Copper also has a very high conductivity. Copper is used in a lot in semiconductor interconnects. Copper tends to be less expensive than silver and gold, so it's popular. Gold has a little bit less conductivity, but is extremely chemically inert, which is great, and that's why gold is often the preferred conductor in high-performance electronics. Aluminum, or as the British would say, aluminium, 3.5 times 10 to the 7th. Iron and mercury are all up there. Carbon, as you can see, is quite a bit less, but it's still a conductor. All right, semiconductors have conductivities that are much lower than conductive materials. Germanium and silicon, you can see they're quite a bit less. Insulators, look at how low the conductivity for these guys are. 10 to the negative 12, 10 to the negative 15, 10 to the negative 17. These things basically don't conduct current at all. The perfect insulator would have a sigma of equal to 0. The only perfect insulator that you could really have is vacuum, where there's nothing. J would be equal to 0 in a perfect insulator. In a perfect conductor, the sigma is going to be equal to infinity, and E is the electric field is equal to 0. As we saw in metals, the electric field is equal to 0. So now we're going to do problems in calculating electrical resistance. So imagine that you have a material and you want to calculate a formula for the resistance. Have you guys done this type of thing before in circuits 1?
Yeah, I don't know.
Did you learn a formula like R is equal to L divided by sigma A? You did?
Yeah.
Okay. And then we cover that again in electronics. So in this class, we're actually going to derive where those formulas come from electromagnetics principles. All right. Now this equation, at first glance, it looks kind of complicated, but we'll do some problems with this that will show you that hopefully that it's not as bad as it looks. So the general definition of electrical resistance is the ratio of voltage over current. All right, so V equals IR, so R is equal to V over I. Right? So in this class, what we do is now, in this class, we've actually learned equations for V and I. Earlier, we learned that the voltage is equal to the negative integral of E dot dl. And just now we did a problem where we learned that I is equal to the integral of J dot ds. All right, so just to make your lives miserable, we're going to take an Ohm's law, something that you love and enjoyed doing problems with because it was fairly straightforward, and now we throw a bunch of integrals into it and make your life miserable. What doesn't kill you makes you stronger. J is equal to sigma E, so that's the difference between these two formulas. All right, so I'm going to teach you the technique of how to solve for these problems, okay? We'll do it in a simple case, and then we'll do it in a slightly more complex case. So the voltage, again, we've done these techniques before. The voltage can be found by performing a line integral of the electric field in the direction of current flow. So that's the trick you have to do. Why is that? Well, we'll see an example of that. We'll see an example that it'll make sense. All right, so that's how you calculate V. You take the line integral in the direction of current flow. So your dl is going to point in the direction of current flow. And the current I, so the denominator of this equation, can be found by taking the surface integral of the current density in the cross-section. All right, so we will look at what that means in a simple problem like this. The resistance of a wire, how many folks remember this equation? The resistance of a wire is equal to L divided by sigma A. Jeremy, you remember? Justine, remember?
Remember the rho L divided by A.
What's that? Oh yeah, very good. Yeah. So I'll use as it says it's rho L over A. So rho is just 1 over sigma. So it's the same thing. So we're going to derive this basic relationship using the fundamental principle that we learned on the last slide. So I'm actually giving you the result here. We're just going to figure out how to get to this result. All right, so there's a lot of arrows and stuff here, but this is basically just a wire. We put a voltage across the wire, okay? So this is your V. Put a voltage across the wire here. This is 0.1, this is 0.2. So this is denoted x1 and x2. This is the y and the x-axis here. So the numerator of the equation is E dot dl. V is equal to negative integral of E dot dl. So the dl is going across, is going in the direction of the current. So if you apply a voltage here like this, the voltage is positive on this side and then negative on this side, then of course your electric field is going to go this way. It goes from high potential to low potential, so from left to right. So that's what your electric field is here. Electric field, and then your dl is going like this as well. Ali. Stretching, okay. The denominator of the equation, that's the I. I is equal to the integral of j dot ds. Okay. That ds is the cross-section, right? So that's why I've shown in this green thing, this is the cross-section where we integrate j dot ds. All right, now, so I'm going to show you how to do this problem and get to that result. So this is finding resistance. All right, so if we want to do this in a step-by-step way, remember R is equal to V over I. And this is equal to the negative integral of E dot dl divided by the integral of J dot ds. This is going to be a double integral because it's over a surface. So if we do this problem step by step, here are my suggestions, okay? Step 1 is you're going to find J as a function of I. So I'm actually going to write that down. Find J as a function of I. Now in this one, it's fairly straightforward. Okay, we start off with this relation I is equal to the double integral of j dot ds. All right, this is where we actually have to use, we have to use our head here and think about geometry. So in this problem, we're dealing with just a regular old wire. All right, now let's just draw our ds here. This is our surface, a cross section. Do we have a situation where the j is uniform everywhere? Is j, so let me be more clear about that. J is looking like this, right? The current density is going through this cross section. Is j equal everywhere? Yeah. This is a case where you're dealing with a copper wire. There's no funny business about different conductivities in different places. This is just a copper wire with same conductivity everywhere. So the j is the same everywhere. And when j is uniform, when this thing is really not a function of where you are, as we found out earlier, this is just equal to what? J times A. All right. So our first step is done. We've found j as a function of I. J is equal to I divided by A, cross-sectional area. So that kind of helps us figure out what this denominator is. Second step is going to be to find E as a function of I. This is also a quick step. What's the relationship? Okay, so
we put as a note like that the currents are uniform. That's why we do that, right?
That's correct. J is uniform. All right. Second step here, find E as a function of I. Now, so we have J as a function of I, and E, there's this very straightforward relationship between E and J. J is equal to sigma E. All right. So E is equal to J over sigma, and so that's equal to I over sigma A. So we found E as a function of I now. So the second step was kind of an intermediate step, which helps us with step 3. And step 3 is where we figure out the numerator there. And step 3 is find V, the voltage, as a function of I. All right. Now V is going to be the integral of E dot dl, the negative integral of E dot dl. So we go from the low potential to the high potential. So remember, we put our voltage source on here like this. And this was the positive side, and this was the negative side. This is x2, and this was x1. So we set up our x coordinate so that x goes in this direction, and y is in the other direction. And this result is going to be fairly straightforward too. So this will be the negative integral from low potential to high potential x2 to x1 of E dot dl.
You mean x1 to x2? Oh,
We're going from low potential to high potential. All right, so this simplifies to the integral of from x1 to x2 of E dot dl. All right, now what is dl in this case?
minus
dl equals x hat dx. Right, remember dl is just depends on what coordinate system you're in. In the Cartesian coordinate system, it's dx times x hat, dy times y hat, dz times z hat.
is it in the negative x?
No. The negative has already been taken into account by the limits of integration. All right. I'm overcomplicating this problem to show you the steps, but if you know that the electric field is the same everywhere, if it's uniform everywhere along the length, then what does this simplify to?
Just the u over.
Well, let's do this. Let's do this since there's a little bit of apprehension here.
I think okay. This
All right. E is I'm sorry.
That would be easier if we had a area just for the area.
Well, let's do the integral. Okay. So the electric field is going to just have an x component. Do we agree? The electric field is pointing in this direction. So x hat times E sub x. That's the electric field. So this is equal to integral from x1 to x2 of E sub x times x hat dotted with dx times x hat. So this becomes the integral of e to the x dx, integral from x1 to x2. The integral of dx is just equal to x. So this becomes ex times x2 minus x1, which is just equal to ex times the length. Okay, I want everyone to remember this because these shortcuts are really important. Let's go back up here. You have to find I is equal to the integral of j dot ds. If j is equal everywhere on the surface you're integrating, if the magnitude of j, if j is equal everywhere, uniform everywhere on the surface, this is the same kind of thing we apply when we're doing Gauss's law. If the field is same everywhere on the surface, then you can just multiply that by the surface area. So in this case, we got I is equal to j times a. Similarly, in this line integral, when you're doing a line integral like this, if the electric field is same everywhere along that line, then just like the previous one, it becomes just the field times the surface area. In this case, it becomes the field times the length. All right, remember that it'll save you time. Let's look at the logic here. We're applying a voltage here, and it's going through a wire of equal cross-section. So that electric field, by symmetry, that electric field is going to be same everywhere in the wire. The wire's conductivity is not changing, the cross-section isn't changing. you're not going to end up with large fields or small fields, like different fields in different places. The field is going to be same at all positions of x. That's why you can do this. So the voltage is equal to the electric field times the length. So I did a lot of math here, but if you know how to use it, this is just a one-step part. All right, so now that we've found this, the last step here is find R equals V over I. So we found V as a function of I. So R is equal to V over I. So let's put in our V first. Our V is E sub x times L and divided by I, so we just have 1 over I here. Now, the E of E sub x that we found, E is equal to J times J divided by sigma, and that's equal to I divided by sigma A. So this electric field, we substitute for that, I divided by sigma A times L, and then we have this 1 over I here. The i's cancel, and we're just left with R is equal to L divided by sigma times A. So the resistance is equal to V over I. So this first portion here, this is V. All right, so we find that R is equal to L divided by sigma A. So let's go back and look at why this was a good approach to doing the problem. In the first part of the problem, we found J as a function of I. That allowed us to find E as a function of I. And that ultimately allowed us to find V as a function of I. Right? If we find V as a function of I, then the resistance is just V divided by I. So the i's end up canceling here. That's how we can get a nice formula for the resistance. The key thing is to find V as a function of I. But to do that, we have to first find E as a function of I, and before that, we have to find J as a function of I. All right, now we're going to do one more problem in the next 15 minutes, and then this problem is going to be a more complicated one. So in this problem, we're going to have a conductor of non-constant cross-section. So this is a coaxial resistor, coaxial cable. And you're asked to find the leakage resistance between the inner and outer conductors of a coax cable with a length L. The inner conductor has a radius A, the outer conductor has a radius B. The medium in between has a conductivity sigma. Now, for this one, what we're doing is, just so everyone is on the same page here, we are trying to measure the resistance between the inner conductor. So you guys have seen coax cables before, right? There's an inner wire and then there's an outer wire. So this is the inner wire here, and the outer wire is kind of like a coaxial shell. It surrounds the inner wire. So what we're doing in this problem is we're finding the resistance between the inner and outer wires. So we're putting a voltage, the voltage sources here, like the one side of the voltage source is connected to the inner wire, the other part of the voltage source is connected to the outer wire. So current is going to flow from the inner wire to the outer wire. So this is more complex than the previous problem. But the way to solve it is actually the same. It's just going to involve a little bit more complexity. Does anyone want to try this problem on your own for a few minutes and see if you can apply the approaches that we did earlier? It'll take a few minutes to, take a couple minutes and see if you can figure it out. I would like to give you more time, so I apologize for a rush here, but I do want to try to get out finish class at the right time. So just take a couple minutes and see if you can figure out the main part. If you figure out just that part, find J as a function of I, if you can figure out that part, you're in great shape. See if you can find J as a function of I. So a key difference in this problem is what the title says. This is an example of a non-constant cross-section. In this previous problem, current was flowing through this wire, and there was always a constant cross-section wherever you were along the current path. In this problem, the current's going from the inner to the outer conductor, but as it's going from the inner to the outer conductor, the cross-sectional area that it's passing through is not constant anymore. That's what makes this problem more tricky.
What coordinate are you working on?
I'm sorry?
Coordinate system?
This will be, what's a great question. What coordinate system do we want to be working in this
It's cylindrical, right?
cylindrical? Right. Any guesses?
So I equals the double integral j dot ds.
Right?
And then we'll take the, okay, here the limits are from, the r is going from 0 to r.
That's right. But that the cross section that you integrate is a different cross section. When you do j dot ds, you don't integrate r. ds is in the r hat direction.
Oh.
Correct.
Okay, so it's,
Let's show this again. I think some of you guys can like figure this out if I gave you a few more minutes, but just in the interest of time, I'm just gonna start going on this, and I'm gonna put this along along the cylindrical system that we're used to seeing, just because I think it'll make things easier. So you have an inner conductor like this. Oh gosh, an inner conductor like this, and then an outer conductor. Okay, these are connected. The inner conductor has a radius A, and the outer one has radius B. All right, so the key point here, the current is flowing from the inner to the outer conductor. So the current is flowing, sorry, this was distracting. I don't know why it's doing that. The current is flowing in this direction. How do I shut this off? The current is flowing in this direction. Gotta shut this off somewhere. So that's the key difference, is flowing from an inner cylinder to an outer cylinder. If we look at this from the top view, it's going to look something like this. This is the inner cylinder. This is the outer cylinder. And the current is going in all different directions like this. Terrible handwriting. All right, so what is our cross-sectional surface? What is our cross-section? What does it look like?
cylinder.
It's a cylinder, yes. Remember in the previous problem when you have current flowing through a wire, the cross-section was just a circle, right? The current density vectors were going through that circle. In this case, it's a cylinder. You can draw a cylinder like this, and that cylinder has a radius r, and the current density is going through that cylinder. So this first step, step 1, find... Why is it doing this? It's really annoying. Find J as function of I. This is a key step. So I is equal to the double integral of J dot ds. All right, now everyone, I want everyone to look at this. These are your JS vectors, okay? And your cylinder, your surface is a cylinder. So what are the two variables you're going to be integrating?
Y and Z.
Correct. So J is going to be some kind of, we can call it JR times R hat. Why are we doing this? This is similar to Gauss's law, okay? We know due to symmetry that the current density is going to be same everywhere along this cross-section, right? You agree that the current density vector here should be the same as the current density vector on the other side. All right, so that's why we're going to call that J sub R, and ds is also going to be in the r hat direction, and what's going to be the magnitude there? We're doing the cylinder, right? So this is the ds vector is going to point away from that surface of that cylinder. So the direction is going to be r hat. What's going to be the magnitude? R d phi dz. That's correct. And the reason for that, think about the cylinder, right? We're integrating over the cylinder. All right, so we're going around that cylinder, that's phi, and then we're going up and down to draw the area of the cylinder, that's z. Whenever we integrate phi, we get r d phi, and then when we integrate z, we get dz. All right, so so this is going to be J times, I should just show you I don't know why I'm spending so much time on this. If we know that J is the same everywhere, all right, we can just say that this is going to be equal to J sub R times the surface area. What's the surface area of the cylinder?
2 pi r squared plus 2 pi rh.
2 pi RH. The surface area of the outer shell of a cylinder is 2 pi RH. Just the outer shell of the cylinder. So I'm just going to put here outer shell of cylinder. Alright, so this is going to be J sub R times 2 pi RH. Alright, we're going to do things quickly. If we know that if we know that the J is the same everywhere, then why bother going through the whole integral? It's supposed to save us time, right? All right, second step. Find E as a function of I. And of course, this is easy now because we know that J is equal to sigma E. So E is going to be equal to J over sigma. In the previous part, we found that J sub R is equal to I divided by 2 pi RH. This is the formula that should be circled here. The next part is E is equal to J divided by sigma, so it's just I divided by sigma 2 pi r h. Remember, h is the height, the length. Okay, everyone with me so far? We're almost done. Third step, just like before, find v as a function of I. All right, this is where we're going to need to do the integral. And this is a step where we actually do need to do the integral. V is equal to the negative integral of E dot dl. Let's remind ourselves what we're looking at here. Okay? We are applying a voltage to the inner conductor, and I'm sorry, that's not correct. We're applying a voltage to the inner conductor, and the outer conductor is grounded. All right, so the current flow is going from the inner shell to the outer shell. So you can see that with the current density vectors that I drew on here. So you really have to understand the symmetry of the problem. So, in this problem, is the electric field going to be the same everywhere? So if we look at the electric field at this radius here, this blue dot here, is the electric field going to be the same as the radius out here? This is the tricky part about this problem. It is not going to. Yeah. As you go from inside to the outside, the electric field actually decreases. So what do you do if you're on a test? What if you don't know if there's symmetry or not? If you're in doubt, then just do the integral. If you are certain that there's symmetry, then you can use these shortcuts that I showed you, just multiplying by the surface area. But you cannot use the shortcut in this case because there's the electric fields are not the same everywhere. So what we have to do is we have to integrate from the inner. So I'm going to redraw this here. This is the inner conductor, and this is the outer conductor. All right, the high potential is connected to the inner conductor, and ground is connected to the outer conductor. Okay, so we are integrating from, we integrate from low potential to high potential, so we're integrating in this direction. All right, from one radius to another. So what is our dl going to be if we're integrating from one radius to another? R hat times dr. And our electric field is going to be what we found up here, I over sigma 2 pi RH. And what's going to be the direction of the electric field? R hat, that's correct. Why is it going to be R hat?
It goes from high to low.
Goes from high to low potential, right? You put the voltage high in the middle and lower on the outside. So the electric fields are going to just point out like this, right? Remember, the electric fields in J, the current density electric fields, they point in the same direction. So if your current density vectors are pointed outwards like that, your electric field is going to be pointed outwards like that too. So E dot dl, we're almost done. Sorry guys, sorry for going over here. So E dot dl, you have R hat, they're pointing in the same direction, so you just have I over sigma times 2 pi RH times dr. Okay, so when we do this integral, we're going to be integrating from low to high potential. So it's negative integral from B to A of E dot dl, and we found E dot dl is equal to I over sigma 2 pi RH. All right, we're integrating from, this is with respect to R, so R from B to R to A. All right, so this is, if we switch the limits of integration, we can get rid of this negative sign. It just goes from, so R is equal from A to B of I over sigma 2 pi H, and this is 1 over R times dr. The reason I took this out is because these are all constants here. All right, and if you remember what's the integral of 1 over R? ln of R from A to B, I over sigma times 2 pi H, and this just becomes ln of B over A, I over sigma 2 pi H. This is voltage as a function of the current. And then the resistance, the last step, R equals V over I. All right, so it's just equal to this thing divided by I. So it's equal to ln of B over A over sigma 2 pi times H. All right, so that's your resistance there. So just so you can see, in the first problem that we did, it was a relatively simple problem because it was constant cross-section. The second problem was non-constant cross-section, and so you had to do a little bit more math, but the basic process, that's 3-4-step process, is still the same. So attack, if you're given a new problem like this, attack it this way, and if you're in doubt whether there's symmetry or not, just go ahead and do the integral. All right, thanks everyone for your attention. I will see you on Wednesday.